Okay, great. Welcome back. We're continuing onward in our discussion of light and optical systems. So, I went over basic properties of simple lenses. We've just talked recently about the eye, the human eye as an optical system, and we ended with explaining that the diopter of the eye, I introduced the notion of diopter, which is the converging power of a lens or an optical system, and I said that the power of the human eye is nearly 60 diopters. So, I want to talk a bit about the imaging properties of a lens, and just in connection with the human eye, as I showed last time. Remember that the light comes in, it's refracted at many places across the cornea through the boundary between the cornea and the outside air, the cornea and the aqueous, the aqueous and the lens and the vitreous. So, an image forms on the retina all the way across this curved area here. So, the retina starts roughly here, goes all the way around and stops here, with the fovea being the place of greatest acuity, where we receive the highest density of information. That part becomes very important, and it's one of the motivations, there are others, but one of the main motivations for eye rotations that we perform. So, we can change the location of greatest visual acuity. So, I want to talk a little bit about images and how they hit an image plane, or in this case, notice it's not going to be exactly what I'm covering, because the engineered systems that we tend to make have focal planes, and we talk about fixed focal distances. Here the retina is curved, and so there will be a curved region that will remain in focus on the outside world as a consequence of that. And so, I'm not going to give sort of all of the geometry of that, but I'm at least going to explain what appears in standard engineering systems. So, let's talk about the imaging properties of a standard lens. So, we have the standard kind of simple lens as we've been talking about here, and I'm going to stop drawing pictures on the board now and just utilize these pre-drawn pictures. So, we have a converging lens, and imagine there is some object that is distance s1 away from the lens appearing in front of it. If we put this object exactly away at infinity, right, so we move this object really far to the left so that it's infinitely far away, we get our parallel lines, and then the image or the focal plane appears exactly at the focal length. But we can bring the object in closer so that instead of being at infinity, it's at distance s1, and then it's going to take longer for the rays to converge because the object is closer, but in some cases they will eventually converge and they will form an image that's further away than the focal distance, which is distance s2. So, the expression for this is 1 over s1 plus 1 over s2 is equal to 1 over f, the focal length. And notice in this picture that s1 and s2 are greater than f. So, for this particular case, we say that on the right side we obtain what's called a real image. I'm going to make a distinction between real image and virtual image on the next slide, but this is called a real image, which means that if we were to place a sheet of paper or a screen here, then an image of the object would actually appear there. So, the light hitting it would form a representation or a kind of rendering, if you like, on the screen in the focal plane. So, we call that a real image. It should be sharp in focus, everything should work out very nicely like that. And if I pull the object away, suppose I hold the screen fixed and then I take this object and start moving it forward or back a bit, then this image will go out of focus. But I could then move the screen to get it in focus again, and I do that according to this formula. Does that seem fine? If this is a nice kind of sanity check, if s1 equals infinity, or take the limiting case where s1 tends to infinity, then what's s2 in this case? F, which is good, right, because that's what's supposed to happen. So if we have S1 equals infinity, that means the object here has been dragged all the way to the left forever, as far as one can go, and then some. And so in that particular case, this should converge in the limiting case to S2 equals F, the focal length. So I just want to point out that relationship, that even though we made a big deal out of the focal length, the focal point, this focal plane, all these things we made a big deal out of that. It's very important. But there's also a range over which the lens can be useful and can produce real images, correct? And the same thing is happening in your eye. It's just that it's curved. So same in some way. Let's say perhaps it's similar because of the curvature of the retina. And in this case, there will be a surface, a two-dimensional surface of locations where you'll get perfect focusing onto your retina of a real image. So there will be, in fact, a real image that appears on your retina. Right. If you get to another case where, let me just draw a simple example here. There may be no solution to this equation. So it may be that, for example, maybe I have focal length, could be 1/2 meter, and I say S1 equals 1/10. So I get 10 centimeters away from the lens. Then if I try to solve this equation here, I get what? 10 plus 1 over S2. I'm trying to figure out where this image would appear. In fact, let me go back a slide. This is what I mean to say. I'm trying to get this to work out. I want to figure out what S2 is going to be. So I make the focal length be 1/2. I make S1, where I place this object, be very, very close. So I put it very close to the lens. It's so close that the rays are diverging a lot. This lens isn't maybe powerful enough to converge them back. They're just too far spreading. So if I do that, I get this, and there's no solution, right? So this tells me that the lens cannot converge the rays. Now if it cannot converge the rays, what if it just does whatever it can? So it may converge them some amount. It may change the divergence a bit and do a little bit of converging, but it's still overall the rays diverge after hitting the lens. We can still do this trick that we did for diverging lenses, which is work backwards and see what the rays would converge to on the left side of the lens, and we get a picture that will look essentially like this. And in this case, we're allowing S2 to be negative. So we allow S2 to be negative, and we still get a solution for this. And this corresponds to a very familiar process called magnification. Right? I pull out a lens and put it up very close to something, and it appears to be larger. However, that's just an appearance to us, and in this case we call this larger object that we get. So again, if you're looking into the lens from this direction now, we put an object up very close to it, but from this perspective the object appears to be very large, right? So that's magnification. So we're using the same kind of lens. There's nothing different about it other than just where I've decided to place the object and where I've decided to view the object from. Now there's one more maybe slightly confusing thing about this, which I should point out. If you decide to use a magnifying glass to look at an object up close, there's still a real image being produced somewhere. This process is still happening in your own optical system of your eye. So when you see the object appearing very large looking through a magnifying lens as it hits the retina, just pay attention to that. That's still going to be a real image. So ultimately your eye has to, when looking at this picture here, and if your eye is over here on the right side looking through this magnifying lens, it's still going to converge the rays anyway so that it produces a real image on your retina, right? But it gives you the illusion that this object is much larger. Okay? So I just wanted to point those things out. Any questions about that?